Hey everybody, what's good? What's going on? JB here, back with another CyberInsight live stream. Today we're doing day 8 of the TryHackMe Advent of Cyber, and this particular task is dealing with smart contracts. So normally I'm like, hey, if you got any questions or comments, throw those in the chat and we'll hit those up. I'll just let you know, I don't know shit about this. I don't know anything about smart contracts. So I'm going to be learning this with you as we go through this. So yeah, if you have anything that you think is important, then you can throw those in the comments and maybe I'll learn something. So yeah, let's dive into this and we'll move through it. There's no actual machine that we need to spin up for this one. There's some task files to download and there's a website that we're going to use this remix IDE. And yeah, let's just kind of go from there, and hopefully this will be fun. So let's see. After it was discovered that the Best Festival company was now on the blockchain and attempting to mint their own cryptocurrency, they were quickly compromised. Best Festival company lost all its currency in the exchange because of the attack. It's up to you as a red team operator to discover how the attacker exploited the contract and attempt to recreate the attack against the same target contract. So what are we going to be talking about? We're going to learn a little bit about what smart contracts are, how they're related to the blockchain, and what's so important about them. We're also going to talk about understanding how contracts are related, what they're built upon, and some of the standard core functions that are within the contracts. Then we're going to understand and exploit a common smart contract vulnerability. So let's see what this is all about. So what is blockchain? One of the most recently innovated and discussed technologies is the blockchain's impact on modern computing. While historically it's been used as a financial technology, it's recently expanded into many other industries and applications. Informally, a blockchain acts as a database to store information in a specified format, and it's shared amongst members of a network with no one entity in control. So it's like a peer-to-peer type of network or decentralized. By definition, blockchain is a digital database or ledger distributed amongst nodes of a peer-to-peer network. The blockchain is distributed amongst peers or members with no central servers, hence it's decentralized. Due to its decentralized nature, each peer is expected to maintain the integrity of the blockchain. If one member of the network attempted to modify a blockchain maliciously, other members would compare it to their own blockchain for integrity and determine if the whole network should express that change. The core blockchain technology aims to be decentralized and maintain integrity. Cryptography is employed to negotiate transactions and provide utility to the blockchain. But what does that mean for security? If we ignore the core blockchain technology itself, which relies on cryptography, and focus on how data is transferred and negotiated, we may find the answer concerning. Throughout the task, we will continue to investigate the security of how information is communicated through the blockchain and observe real-world examples of practical applications of the blockchain. Okay. So one of the key components of how this all works is smart contracts. And so here they're talking about a majority of practical applications of blockchain rely on a technology known as a smart contract. Smart contracts are mostly commonly used as a backbone of DeFi applications or decentralized finance applications to support cryptocurrency on a blockchain. DeFi applications facilitate currency exchange between entities. A smart contract defines the details of the exchange. A smart contract is a program stored on a blockchain that runs when predetermined conditions are met. So it kind of sounds like an application or a script. Smart contracts are very comparable to any other program created from a scripting language. Several languages such as Solidity, Viper, and Yule have been developed to facilitate the creation of contracts. If I jacked up how any of those are pronounced, I apologize. Smart contracts can be developed using traditional programming languages such as Rust or JavaScript. At its core, smart contracts wait for conditions and execute actions similar to the traditional logic that we see in other scripting. A functionality of a smart contract. Building a smart contract may seem intimidating, but it greatly contrasts with core object-oriented programming concepts. Before diving deeper into contract's functionality, let's imagine a contract as a class. So if you don't have a background in a little bit of programming, then you might be lost a little bit as far as object-oriented programming concepts and what a class is, but hopefully they kind of tie this together. Depending on the fields or information stored in a class, which I think is just like, well, we'll see. You may want to, let me say that again. Depending on the fields or information stored in a class, you may want individual fields to be private, preventing access or modification unless conditions are met. A smart contract's fields or information should be private and only accessed or modified from functions defined in the contract. A contract commonly has several functions that act similarly to accessors and mutators, such as doing actions such as checking a balance, depositing, or withdrawing currency. Once a contract is deployed on a blockchain, another contract can then use its function to call or execute the functions we just defined above. So if we controlled contract A, which is this here, and contract B wanted to first deposit 1 Ethereum and then withdraw 1 Ethereum from contract A, contract B calls the deposit function of contract A. Contract A authorizes the deposit after checking if any predetermined conditions need to be met. So what are those predetermined conditions? I guess that might depend upon the contract, and that might be where things kind of get a little precarious, perhaps. Contract B calls the withdrawal function of contract A. Contract A authorizes a deposit if the predetermined conditions for the withdrawal are met. I think I just said that twice. Contract B can execute other functions after the ether is sent from contract A, but before the function resolves. Okay, so it's like it has an open window and can execute other functions while the original function hasn't closed out yet. So we have a withdrawal, there's a balance, 200 ETH, the contract B balance is 1. Conditions is balance is not empty, which is correct. And then send ETH to contract B balance is 0, and that 1 ETH goes over back to contract B. Contract B can execute other functions after ether is sent from contract A, but before the function resolves. So you could withdraw other calls, and then the other function resolves, I guess is what that's saying. So that's cool and all that, but how do vulnerabilities in smart contracts occur? Most smart contract vulnerabilities arise due to logic issues or poor exception handling. All right, so we're talking about if you're able to do something outside the bounds of what is supposed to be permitted, and then depending upon what the exception or lack of exception handling is there, you might be able to get another reaction. Okay. Most vulnerabilities arise in a function when conditions are insecurely implemented through the previously mentioned issues. Let's take a step back to contract A in the previous section. The conditions of the withdrawal function are the balance has to be greater than 0 and send Ethereum. At first glance, this may seem correct, but when is the amount to be sent subtracted from the balance? Okay, so they're saying if it's not subtracted from the balance, then the balance is going to just appear to be the same as what it was before, and you could continue to just hit it. Referring back to the contract diagram, it is only ever deducted from the balance after the Ethereum is sent. Is this an issue? The function should finish before the contract can process any other functions. Okay, so it is only ever deducted from the balance after the Ethereum is sent. So until that function closes out, you can continue to make requests for a withdrawal, maybe. And so you're just going to be able to keep pulling that out. Okay, let's see if that's what they say. But if you recall, a contract can consecutively make new calls to a function while an old function is still executing. Attacker can continuously attempt to call the withdrawal function before it can clear the balance. This means that the predefined conditions will always be met. A developer must modify the function's logic to remove the balance before another call can be made or require stricter requirements to be met. Okay. So the re-entrancy attack. In the above section, we informally introduced a common vulnerability known as re-entrancy. Reiterating what was covered above, re-entrancy occurs when a malicious contract uses a fallback function to continue depleting a contract's total balance due to flawed logic after an initial withdrawal function occurs. We have broken up the attack into diagrams similar to those previously seen to better explain this. Assuming that contract B is the attacking contract and contract A is a storage contract, meaning the one that has the money, contract B will execute a function to deposit, then withdraw at least one ether. This process is required to initiate the withdrawal function's response. So the attack functions require the value greater than or equal to 1, deposit 1 ether, withdraw all ether from the account. So on contract A, has 200 ether, withdraw functions require balance greater than 0, which it has, send the account balance to the contract that requested the withdrawal, set the account balance to 0. Notice the difference between the account balance and the total balance in the above diagram, so 200 to 1. The storage contract separates the balances per account and keeps the account's total balance combined. We are specifically targeting the total balance. We do not own, let's say that again. We are specifically targeting the total balance we do not own to exploit the contract. Let's see. So attack function stays the same here. Again, it's a 200 and 100. Withdraw function greater than 0. Set the, so this is kind of saying the same thing, but then you're also getting the money being deposited back. Or I should say being withdrawn, coming back. At this point, contract B either drops the response from the withdraw function or invokes a fallback function. A fallback function is a reserved function in Solidity that can appear once in a single contract. The function is executed when the currency is sent and no other context or data. For example, what is happening in this example? The fallback function calls the withdrawal function again, while the original call to the function was never fully resolved. So it's like the window's open and you're able to just keep pulling stuff out. Remember, the balance is never set back to 0, and the contract thinks of ether as its total balance when sending, not divided into each account. So it'll continue to send currency beyond the account's balance until the total balance is 0. And this is kind of what this picture here is showing, is this withdrawal with a fallback function. Because the withdraw function sends ether with no context or data, the fallback function will be called again, and thus an infinite loop can now occur. Now that we've covered how this vulnerability occurs and how we can exploit, let's put it to the test. We've provided you with a contract deployed by Best Festival Company in a safe and controlled environment that allows us to deploy contracts as if they were on the blockchain. All right, never done this before, so this is kind of cool. This will be exciting. So practical application. We've covered almost all of the background information needed to hit the ground running. Maybe. Let's try our hand at actively exploiting a contract prone to the re-entrancy vulnerability. So pretty much what we covered here, where it's not going to close out of that other function, and then you have a fallback function that can just continually, I guess, pull out the rest of the ether. For this task, we'll use the Remux IDE, which offers a safe and controlled environment to test and deploy contracts as if they were on the blockchain. So it's not on the blockchain. It's kind of like a sandbox environment. Download the zip folder attached to this task and open Remix in your preferred browser. We have provided you with 2 files. One gathered from the Best Festival Company used to host a cryptocurrency balance, and another malicious contract that will attempt to exploit the re-entrancy vulnerability. Both contracts are legitimate Solidity contracts, but no worry if you need help understanding the program syntax behind each. They follow the same functionality and methodology we covered earlier up above, just translated to code. So getting familiar with the Remix environment. So we're going to open that up. The left side, there will be a file explorer, a search, a compiler, and a deployment navigation button, respectively from top to bottom. We'll spend most of our time in the deploy and run transactions menus, as this allows us to select from environment, account, and contract. So we have this here. I actually already downloaded and added these in. So we just start over here, File Explorer. If we want to add in those files, you just hit this load a local file into current workspace. And then I uploaded these two .sol contracts here. And so we can kind of look through this if we wanted to. We will store the target contract to exploit in a state variable called ether store. When we deploy this contract, we will pass in the address of the ether store contract. Fallback is called when ether store sends ether to this contract. Okay. And then this is the regular contract. So this would be kind of like the contract A that we looked at. And this is the one that would need to have some better rules in place as far as deducting from the total balance or closing out functions before allowing the next function. And I apologize for this. I'm doing this in Safari. I think these should have icons, so we can't really see what these are. So we've got File Explorer, Search in Files, the compiler, deploy and run transactions, static analysis, unit testing. Okay, so let's see what they wanted us to do. Import the necessary contracts. So navigate to File Explorer, default workspace, load local file, which I already did for both of those. From here, you can select the necessary .sol files to be implemented. We provided you with etherstore.sol and attack.sol. All right, so compiling the contract. So next step is to compile the contract. So we're going to navigate to the compiler option on the left-hand side. We're going to select whatever this is from the drop-down compiler menu. I think that's, we'll see. And now you can compile the contract by pressing the compile button. You can ignore any warnings you may receive. So we can do this. We're going to highlight this. We're going to go to compile. And that's what we have here, compiler. We're going to compile etherstore.sol. Okay, so now it's kind of done its thing. It looks like we have like static analysis that we could do on that contract now that it's compiled. But let's go back and compile the attack one as well. We're going to go back to the compiler. That's the same, compile attack.sol. So we've loaded the contract files, we've compiled them, deploying and interacting with contracts. Now that we have the contracts compiled, they are ready to be deployed from the deployment tab. To the right is a screenshot of the deployment tab and labels that we will use to reference menu elements as we move through this. So we have the environment, the specific account, the value. We want to make sure that that's probably set to ether because there's probably a few different options. The specific contract that we want to deploy, the deploy button, an address that we want to point to, and then so let's just see what they say here. So first we must select a contract for deployment from the contract drop-down, label 6. We should deploy the ether store contract or target contract to begin with. So for deployment, you only need to press the deploy button. So we're just going to go back. Okay, we're going to leave all this and we're going to pick the ether store and we're going to deploy. Okay, when we did that, it deployed contracts down here. We have a balance of 0 ether. Since this is all made up, we probably can F around and maybe give ourselves some ether. Let's go deposit 10 ether. Oh, and look at that. I just mentioned we should probably have it actually on ether, and it wasn't, so let's switch that. Let's try that. Deposit 10 ether. There we go. Now we can see our balance is that. We also, it's kind of like this debug output down here that lets you know what's going on. It's kind of cool. We can move that up a little bit. All right. let's see what they want us to do after that. We can now interact with a contract underneath the deployed contracts. To test a contract, we can either deposit Ether into the contract to add to the total balance. To deposit, oh, that's what we just did. To deposit, insert a value into the value box and select the currency denomination from the dropdown. Once this is complete, you can hit deposit by hitting number 10 deposit. Now I'm pressing the deposit button. This is a public function we are calling just as if we were calling another contract, just as if it were another contract calling the function externally. Okay. We've now successfully deployed our first contract and used it. Man, we're killing it. Killing the game. Just crushing it. You should see the balance update, which we did. Now that we have deployed our first contract, switch to a different account. So we're going to drop down label 2 and select a new account, repeat the process. This time you will be exploiting the original contract and should see the exploit actively occur. We have provided a summary of the steps to deploy and interact with the contract below. So we're going to select a new account from 2, select the contract we want to deploy, which is going to be the attack one. We're going to deploy it by pressing the deploy button. But we need to provide a reference to the contract we are targeting before deploying the attack. So we're going to copy that. Should be able to copy it from like right here. Let's see. So let's go new account. Let's go attack. Sol, we're going to copy. So this is the Ether store address. So we're going to copy that. We're going to put that here. So we have new account, contract that we're doing, which is the attack one, which one we're connecting to, right? Which is the Ether store one, which is the one that has the exploitable code. We're going to hit deploy. Okay, so that popped that down here. We can open this up. And then you see here it actually has the attack function in that. And you see, you can kind of see how these functions actually tie back to what these buttons are, right? So we're seeing that. So we want to attack. So if we just hit the attack button, what is there? There was a little bit over 10 Ether in the Ether store one. So let's see. I think we needed to like actually send something. Confirm the account was deployed and attack. So let's see if we actually need, we can just hit attack. Yeah, so we need to actually, let's set a value here of 1, and then we're going to attack. I mean, it must be working because it's taking a little bit of time. And we just saw our balance go from 0 to 11. And it looks like we got that. If we go back and we look at the Ether store, we see that it pretty much we took all of it for the most part, except for that little that 0.0000001, which I accidentally added in there with the other thing that wasn't Ether. So yeah, so that did that, and then it popped up this flag, which we'll probably need, I assume, for something. So let's go see if that wraps up what they wanted us to do. We executed it. Interact with the contracts function. Note that the most functions require some form of value input to execute the function properly. Exactly right. When I tried to do it without having the 1 Ether there, it did not work. So let's see what they want us to do. If you're not already completed, download the zip, open remix. We did that. What is the flag found after attacking the provider's Ether store contract? I think that's it. And are we up for a little challenge to celebrate day 8? They got these easy challenge rooms. Not sure what those are on, but I'm good for today. Don't know about you. But yeah, so that was kind of interesting. I've never used Remix before. Never compiled a crypto contract and then actually exploited one. So that's kind of cool. Appreciate everybody dropping in. This is day 8. Looking forward to day 9. We'll see what's going on with that. But yeah, make sure you smash the like button, subscribe to the channel, all that other stuff. Saw some folks drop in. Appreciate everybody coming by and saying hi. So yeah, I will chat with you tomorrow. All right, bye.